How is it that only 3 students joined the class? There are 9 of you. Let's wait for your classmates. Only 3 students. Though this is my first class for this academic session, I was expecting more students to join the session. We'll wait for a few minutes. Okay, now that 6 of you are here, I think we can start our lecture. So as usual for this class, you can just type your roll number in the chat box. So I hope you can see my screen here in this second semester course. I will be teaching part of this electronics and instrumentation paper, that is your course number GP2 CC10. And Dr. Monpuya will be teaching the first 2 units. I will be teaching the third and the fourth units. So the third units is operation amplifiers, which I know that some of you are already familiar, particularly those students from physics background. But there are some of you who are from other backgrounds, like geology backgrounds or from other university. So we have to go through this op-amp once again, and once we complete op-amp, then we can move on to equip your unit 4, which consists of this instruments like CRO and LEDs, LCDs and all, right? So these are the experiments which we are going to do in this course as well. So we will be having experiment like JFET, UJT transistors, and single and dual stage RC coupled amplifier, and experiment with logic gates, flip-flops, triple five timer, an integrator and differentiator. And we have purchased some equipments for this. So this experiment, we can do it probably in offline mode. So I don't know how the SOP will develop. Hopefully, when we can have a normal class, we can do this practical. So these are very few experiments that we are going to do, and we can quickly finish it up. No issues with this. So when we talk about op-amp, if you look at the particular wording for a name given to this particular amplifier, this is an op-amp. Op-amp means operational amplifier in full form. So operational means that kind of amplifier which can perform mathematical and algebraic operation like what is that? Summation, subtraction, integration, and differentiation and all. So uh, when an amplifier is designed such that that amplifier can perform such kind of operation, that particular amplifier is called operational amplifier. And this operational amplifier is designed on a certain silicon chips. So uh, that chip is called integrated circuit IC. So in that integrated circuit, within that integrated circuit, that amplifier is designed like the way shown here in the figure. If you look at this figure here, this is the actual circuit diagram of an operational amplifier, how it is fabricated within your integrated circuit. So this operational amplifier, it has two input terminals. One here, I circle here, this is called the inverting input. And here, the number given here for this inverting input is number 2. So this number 2 is called pin. Pin means path identification number. So pin number 2, in this pin number 2, that is, if you look at this circuit here, this is your transistor, right? Q2 is a transistor, Q4 is a transistor, Q1 is a transistor. So all these transistors are connected with these resistors like 1 kilo ohm, 50 kilo ohm, 1 kilo ohm and all. So transistors and resistors, as well as this capacitor, this is 30 picofarad capacitor. So transistors and capacitors, network of transistors and capacitors are fabricated within a very small silicon chip. So all these components that are shown here are fabricated on a very small silicon chip using a technology called what is that, large scale integration circuit technology and all. So within that integrated circuit, one can design with the existing technology available with us nowadays in any industry. They can design this kind of circuit in a small silicon chip. So here is a transistor. If you remember, this is the circuits, this is the symbol for a transistor. Transistor has three terminals. One terminal is called emitter, another terminal is called base, and another terminal is called collector. And usually on the, not usually, always actually, always on the emitter terminal, arrow is provided. So if you have an arrow like this, an arrow gives you the direction of actual flow of current. So if a direction of actual flow of current is towards the emitter from the base, then that means this is your NPN transistor. That is, your emitter is N-type semiconductor, and the thin layer base is, this is your emitter is your N-type semiconductor. The thin layer base is your P-type, and the thick and the broad collector terminal, and the broad layer is called your collector terminal, which is also N-type, NPN transistor. Okay, so I hope you are all familiar with the operation of a transistor by now. Here, the input at this inverting input or at this path identification number 2 is supplied to the base of the transistor Q2 here. And We have another input terminal which is called pin number 3 here, part identification number, and that input terminal is called non-inverting input. Here, the non-inverting input to this transistor Q1 is also supplied at the base here. So arrow here means this is your emitter, this side is your emitter, this side is collector, and the other side is collector, right? So you have two input terminals, inverting and non-inverting, as shown here in the figure. And you see, in this circuit, there are around, yeah, I think there is 22 transistors. There are 22 transistors here, which are fabricated within a small silicon chip here, as I mentioned before. And these are the two input terminals, pin number 2 and pin number 3. And your output is taken here from this terminal, which is called pin number 6, part identification number 6. And if you remember the operation of a transistor, in order to operate the transistor, you need to turn on your transistor. In order to turn on your transistor, you need to forward bias the terminal between emitter and base, and reverse bias the terminal between base and collector. Reverse bias between base and collector, forward bias between emitter and base. So in order to do that, we need to supply what is called the biasing potential. The biasing potential is supplied to pin number 7 here. Pin number 7 gives you the DC power. So from pin number 7, we provide DC power or DC voltage, positive DC voltage. And with the resistor network and all, some of these transistors may be turned on, and that is turned on means the transistor will be in the active region of operation, and some of the transistors may be turned off as well. And also another DC power supply is provided at this pin number 4, part identification number shown here in the figure. So by supplying DC positive voltage as well as DC negative voltage between pin number 7 and pin number 4, we can turn on your transistors in this silicon chip. And here you see that the resistors and all, they will provide the biasing network. If you remember, in the undergraduate section, we discussed voltage divider bias system and all, for those of you who have a physics background. And in addition to this power supply terminal, we also have another terminal, another two terminal actually, called offset terminal. So pin number 1 and pin number 5 are for offset. So they are called offset null terminal. Here you see the pin number 1 and pin number 5 in this complete circuit diagram of your operation amplifier. So by supplying voltages between at this pin number 1 and pin number 5, we can nullify any input offset or output offset. So we will talk about offset later on. So these are the terminals for offset, right? So this is the circuit symbol or circuit diagram of an operation amplifier. So like I said before, particularly this particular circuit is for IC741. So IC741 is one of the operation amplifier transistors which are normally used for our laboratory purpose, but for your other applications like military applications and maybe your amplifier applications and all, there are some other ICs which can operate at extreme temperatures, like for military devices and all. If you're going to use this kind of op-amp, the IC, the integrated circuit used, has to be able to it has to be able to bear the extreme weathers, like some of the military equipments might be operated in a Himalayan mountains or maybe in desert as well. So depending on the design of your IC, there are certain operating temperature range and all. So this IC, which is shown here, IC741, is not used for such kind of purpose. And usually there are some other ICs which are manufactured by other companies, like see, if in your IC this, if there is an M here, M means it stands for military purpose. Okay, M stands for military purpose. So M stands for military purpose. And the temperature, the working temperature ranges between -55 degrees Celsius to 125 degrees Celsius. IP, in if in your IC, if there is an IP stands for industrial purpose with an operating temperature range and all. And C identifies the operating temperature range. So CP means commercial purpose, right? So CA here, the first two alphabets in this IC here, these are the codes for the devices, like uh, CA is for RCA, or AD is RCA, AD is for analog devices, LM is for National Semiconductor Corps, and mu ampere, mu A is called Fairchild. So by looking at the IC number here, one can tell which company manufactured uh, which company manufactured that device, or uh, whether it's a military purpose, or industrial purpose, or commercial purpose. So usually for laboratory we are going to use CP. So this is for the commercial purpose. Okay. Now, so like I said, this is a circuit symbol. So simply you write sort of triangle like this, and as shown in the previous slides, where you can see here the detailed circuit diagram of your op-amp. Uh, in this circuit symbol, simply we put one of the input terminal as inverting input, which is called pin number 2. Another input terminal, which is non-inverting input, pin number 3 here. And as the name implies, inverting input means in this circuit symbol you put a minus sign. So inverting input means if you feed any signal there at the inverting input, it will reverses the sign, or there will be a 180-degree phase change. So if you like supply a positive DC signal, DC voltage, in the output section, it will become negative DC signal. Or if you supply sine wave here at the inverting input, the output will be cosine wave. So there will be a 180-degree phase change always when you supply input to the inverting input terminal. And non-inverting input terminal, pin number 3, it's designated with plus sign here in this circuit symbol. That means there is no phase change, or there is no change of sign. Okay. And here pin number 7 and pin number 4, like I have shown here in the circuit diagram of op-amp, the internal circuit diagram of op-amp. Pin number 7 and pin number 4 are positive terminal as well as negative terminal. And pin number 6, like already shown here in the previous slides, this is also your output terminal. Okay. And there are certain designs, like metal can design, this kind of circular can design for an op-amp, where if you have a certain knobs or certain marking here, from the certain marking, the first pin, the first metal rod, or I mean the first uh, tentacle, the first leg of this metal can, on the right side of this knob or tap here in this metal can, there is pin number 1, counted as pin number 1, second one as pin number 2, 3, 4, 5, 6, 7, 8. So there will be 8 pin metal can. And like I've shown here before, pin number 2 and 3 are the inverting and non-inverting input. Pin number 6 are pin number 6 is the output. Pin number 7 and pin number 4 here, they are the plus VCC and minus VCC for operating the transistors in that op-amp. And your pin number 1 and pin number 5 are for your offset null, which I will explain later. And pin number 8 is your pin number 8 is actually this is no connection. Okay, so in pin number 8, no, nothing is connected in a transistor. This is just an empty pin. Okay, and so there's another design also called DIP package design, which is sort of rectangular uh, shape as shown here. And if there is certain knobs or certain marking here, so the first leg adjacent to that, the first tentacle of such um, IC integrated circuit, uh, the first tentacle, the first leg here is called pin number 1, the second is pin number 2, 3, 4. So that means pin number 2 and 3 are the two input terminals. And similarly, over here you will have pin number 6 as the output terminal and all. All right. So this is how it looks. This is the actual design here. Okay, this is the actual uh, picture of your IC741. So here you see that there is a grooving here and there is a certain circular marking here. So the first leg adjacent to this is called your pin number 1, part identification number 1, and this will be your pin number 2. This is your pin number 3, this is your pin number 4, and behind this there will be 5, 6, 7, and 8. So this is the uh, representation in so from this representation, one can clearly see how the pins are arranged here in this IC741. So pin number 2 is here, which is inverting terminal. So there is a minus sign here, pin number 2, 3 non-inverting. Similarly, pin number 6, outputs 7 and 4, the two terminals for supplying your DC power. And pin number 1 and pin number 5 are offset null. Pin number 8 is designated as NC. NC means no connection. All right. So let us see the characteristics of operation amplifier. The first characteristics of an operation amplifier is a very important one. In this particular characteristic, if you know these characteristics, you will understand the operation of your op-amp as well. Like as you see here, the first characteristic states that op-amp is difference voltage amplifier. Difference voltage amplifier means you have two input terminals. Op-amp will amplify the difference in voltage at the two input terminal. Okay, it will amplify the difference in voltage at the two input terminal. So the output will be input output relation will be like this. So the output pin number 2 is inverting input, pin number 3 non-inverting. Non-inverting input signal is designated usually as V1. Inverting input signal is designated as V2. Output is designated as V0, which is taken from pin number 6. And these are your plus VCC, pin number 7 and pin number 4 here. So difference amplifier means your output voltage will be gain of your amplifier multiplied with the difference in voltage at the two input terminals. Okay, output voltage is gain multiplied with the difference in voltage at the two input terminals. So whatever difference in the voltage at the two input terminals, it will be amplified with a gain of A. So for an ideal operational amplifier, the gain A is infinite. But for practical op-amp, that is mu A here means it is manufactured by Fairchild. Okay, C means operating temperature here. The operating temperature. So when there's an in that IC number, when IC is written there, so that IC can operate between 0 to 70 degrees Celsius only. Okay, so practical op-amp like the one manufactured by Fairchild company, that is mu A 741C, this IC usually has a gain of 200,000. It has a gain of 200,000. But you know, even if this IC has a gain of this 200,000, the output cannot go beyond the DC power supplied to your op-amp. The DC power, the standard DC power supplied to op-amp is pin number 7 is plus 14 cc. So plus 15, usually 15 volt is supplied. And for a negative DC power terminal, that is pin number 4, like I described before, this is also usually supplied for plus minus 15 cc. So minus 15 volt, plus VCC is plus 15 volt, minus VCC is minus 15 volt. So when we supply this kind of DC power, even if the gain is 200,000, output voltage cannot suit or cannot exceed your DC supply. Otherwise, it will be some kind of perpetual energy source. So, due to conservation of energy, whatever output you're having from this op-amp cannot exceed the power, the electrical power or the electrical voltage given to pin number 7 and pin number 4 here. So, for example, if your voltage at the pin number 1 is, for example, 0.02 volt, and if your voltage at this is 0.04 volt. Now, if you look at this VD, VD means 0.02 volt minus 0.04 volt. So this will be minus of 0.02 volt. Minus of 0.02 volt. Now, from this, if you calculate your output voltage, and if you are using this 741 IC manufactured by Fairchild company, the gain is 200,000, and multiply with this VD. VD value is minus of 0.02 volt. So this is going to be minus of how much? If you multiply this, it's going to be 4 into 0.02 means 4,000 volt, isn't it? This is going to be minus of 4,000 volt. But as I said before, due to law of conservation of energy, you cannot just create a voltage out of nothing, right? So if you are supplying plus 15 volt and minus 15 volt between this terminal, like pin number 7, pin number 4, these are the voltage given to this op-amp, the electrical energy, electrical voltage signal given to this op-amp. So it cannot exceed this minus 15 volt or plus 15 volt. In the minus side, it cannot exceed minus 15 volt. In the plus side, it cannot exceed plus 15 volt. So even though from this formula, due to the large open loop gain of 200,000, you are supposed to get this, the output cannot exceed your minus 13 volt. So the negative signal in the output terminal, the saturation voltage or the voltage which the output voltage cannot exceed is usually minus 13 volt, and the voltage which the output voltage V0 cannot exceed is plus 14 volt. Okay, so depending on whether V1 is greater than V2 or V2 is greater than V1, the output voltage will swing between minus 13 volt and plus 14 volt, not beyond that. Okay, not larger than that. Now, another characteristics of an op-amp is called input offset voltage. Okay, input offset voltage. So input offset means say even if you connect, say even if you connect the same voltage here at the two input terminals, and even if you connect the same voltage at the two input terminals, same value, because of the like certain circuit defects here. If you look at this, these are the inverting input. This is the complete circuit diagram. This is non-inverting input terminals, complete circuit diagram. Now, and we know that already that your this thing, op-amp is a difference voltage amplifier. Whatever voltage, whatever difference in voltage at the two input terminals will be amplified, right? But even if you connect 0 volt here, if you even if you connect 0 volt here between these two, even if you connect 0 volt here, the output voltage may not be zero. Okay, the output voltage may not be zero. So the possible reason is that uh, the two input terminals here, pin number 2 and pin number 3, they consist of certain transistors like Q2, Q3, and another Q3, Q4 here, and also these are resistors and all. So due to certain manufacturing defects here at the transistors and all, uh, there may be certain kind of imbalance or not balancing, right? So if the two input terminals, pin number 3 and pin number 2, are not perfectly balanced, if there is a offsetting, right? Offset means in certain quantity which are not balanced. Okay, so if the two input terminals are not balanced, even if you supply the same voltage or 0 volt each here, you will still have non-zero output voltage. Ideally, VD is what is amplified, right? VD minus V2. If V1 is equal to V2, then your VD is supposed to be zero. But it is possible that due to certain circuit manufacturing defects, even if V1 is equal to VD, V1 equal to V2, VD might not be zero. Okay, VD might not be zero. So the offsetting at the two input terminals is called input offset voltage. And the maximum permissible input offset voltage is that is 6 millivolt. If the offsetting at the two input terminals V1 and V2 is beyond 6 millivolt, then that op-amp will not operate properly, or it will not it will not be able to provide you a desired output voltage. Okay, it will not be able to provide you a desired output voltage. So therefore, maximum permissible value is defined as 6 millivolt. But in an ideal op-amp, input offset voltage for an ideal op-amp has to be zero. Okay, for ideal op-amp it has to be zero. Ideally, there should not be any mismatch at the two input terminals or offset at the two input terminals. But in practical amplifier, we can have certain input offset due to manufacturing defects there. So that is called your I mean your maximum permissible value is 6 millivolt. Okay, and there's this thing called output offset voltage. Output offset voltage means if you connect uh, to I if you connect the two input terminals, pin number 2 and pin number 3, to 0 each or identical values, and ideally again similar to input offset, ideally the output voltage has to be zero. But uh, similar to your input offset, in the output circuit also the output voltage might not be zero. Due to certain defects in the output circuit also, output voltage might not be zero. Okay, so there may be a certain error in the output circuit. Such kind of error or offset means some kind of mismatch in the output terminal. Pin number 6 is known as output offset voltage. So this output offset voltage, it can be corrected using this potential divider network. If you connect this potential divider, this is potential divider of 22 kilo ohm. If you connect between pin number 1 and pin number 5, and if you take another voltage here at pin number 4, that is your negative VCC of minus 15 volt, by adjusting this potential divider, uh, you can uh, you can set it to 0 volt here. You can set your output voltage to be 0 volt when the voltage is connected pin number 2 and 3 are both zero. So this kind of offset or mismatch at the input and offset, output section, it can be corrected using this pin number 1 and 5, which are the terminals known as offset null terminals, right? 1 and 5 are offset null terminals. Now, another characteristics of op-amp is what is called differential input resistance. Differential input resistance means the resistance that is appearing at the two input terminals, pin number 2 and pin number 3. The resistance between pin number 2 and pin number 3. There is a certain resistance appearing between pin number 2 and pin number 3 that is called differential input resistance. For ideal op-amp, the resistance between pin number 2 and pin number 3, suppose this is your resistance, the resistance appearing between pin number 2 and pin number 3 is infinity for ideal op-amp. Input resistance between pin number 2 and pin number 3 is infinity. For practical op-amp like 741, the resistance between pin number 2 and 3 is usually 2 mega ohm. So these characteristics are something which you need to remember for op-amp, right? So there is this thing called output resistance. So the resistance that will be appearing across the output circuit is called output resistance in this op-amp. So for ideal op-amp, the output resistance is again 0. For practical op-amp, the output resistance is 75 ohm. Okay, 75 ohm. I will end my lecture now. So this is our first class. We only have 2 minutes now. If you have typed your attendance, I think we can end the session. And maybe from the next class, we can have a more regular and maybe longer lecture. Okay. So let's end our session now. This is just an introduction to op-amp.